Hello and welcome to the February webinar from the IEA Clean Coal Centre. My name is Benedicta Brox and I'm the Communications Officer here at the IEACCC. Our monthly webinars are based on our technical reports available from our website www.IEA-coal.org. Residents of member countries and employees of sponsoring organizations can download our reports at no charge after a one-off registration. Please visit our website for details. The subject for today's webinar is water conservation in coal-fired power plants. I will now hand you over to Anne Carpenter.
Right, good morning everyone, and welcome to this talk on water conservation in coal-fired power plants. As Benedicta mentioned, this webinar is based on a report that I've just finished, and this report will be published shortly. The report continues a series relating to water and the power generation industry. The first one examined water availability and policies for the coal power sector in China, India, South Africa and the USA. These are the four top thermal coal consuming countries in the world. As you can see from this figure, they all have water stress regions. The second report looked at alternative non-fresh water sources for power plants, and these are sources such as municipal wastewater and mine water. I've given webinars on both these reports and these are still available for viewing. That is, of course, if you're interested. The vulnerability of the power generation industry to constraints in water availability is widespread and growing. As you can see from this figure, significant areas of almost every continent are currently facing a high level of water stress. The darker the orange and red, the more stressed the region is. Now, regions where water is scarce face obvious risks, but even regions with ample resources can experience constraints due to droughts, heat waves, seasonal variations and other factors. Now, for example, last year a number of power plants in India had to temporarily shut down due to a lack of water. And this included all 5 units at the 1600 megawatt Farakka coal-fired power plant in West Bengal. And the power plants in the northeast region of the USA, where water is actually abundant, they are facing issues of water quality and temperature. Power plants here have had to close down at times to ensure they do not exceed the permitted water discharge temperature. So the number of power plants affected is likely to increase in the future, especially with the growing energy demand in many parts of the world. Consequently, the pressure on power plant operators to conserve water will increase. I'm going to begin this talk by looking at the main places where water is lost and added within a power plant. I'll then describe techniques for recovering water from coal and ways of conserving water in ash handling and pollution control systems. I'll then look at recovering water from the flue gas, and finally how water can be saved in the cooling systems. Water is essential for power generation. Heat from combustion of coal is used to convert water into high pressure, high temperature steam, which is expanded through a turbine to produce electricity. There are many different designs for pulverised coal-fired power plants, and this figure just illustrates one design with its associated water steam path, and that is the path shown in the top part of the figure, and then there's the flue gas path which is shown in the bottom half. Now, water exits the system in various ways. These include the unavoidable losses. For example, part of the recirculating water in the cooling tower evaporates and the resultant water vapour is lost to the atmosphere when it exits through the top of the tower. There are also losses in the formation of products such as gypsum from the wet flue gas desulphurisation scrubber. And blowdown is another loss. Blowdown is necessary to preserve water quality and to remove impurities from the various recirculating streams. This includes the boiler feed water, FGD streams and cooling water. and then water is also lost when handling products such as in ash sluicing. Right, I've included this figure to give you an indication of the amount of water that is withdrawn from a water source and consumed within a power plant. It is for a 500 megawatt subcritical plant firing bituminous coal. The plant layout is basically the same that was shown in the previous slide. As you can see, the cooling system, which is a wet cooling tower, consumes the most water, followed by the FGD scrubber, which here employs a wet limestone process. Right, I now look at water recovery from coal. Drying the coal before it is combusted and recovering the moisture could provide water for internal use. Lignites, for example, can have inherent moisture contents as high as 70%. In conventional power plants, the drying takes place within the mill, as shown in this figure. But using a high-grade heat to dry the coal and passing all the evaporated moisture through the boiler results in lower power efficiencies and higher CO2 emissions than from plants firing coals with a lower moisture content at similar steam conditions. So instead, the coal could be dried, preferably using low-grade heat, and the evaporated moisture captured from the mill exhaust. Or the coal could be pre-dried and the moisture captured before the coal enters the mill. Both options would also result in a lower flue gas volume and consequently lower water consumption in wet cooling towers and the wet FGD systems. Moreover, the plant's thermal efficiency would increase, and the efficiency could increase by about 1 percentage point when it's retrofitted to an existing lignite-fired power plant, and by some 4 to 5 percentage points on a new power plant that employs a dry cooling system. Well, these values are on a lower heating value basis. One technology being developed in China to cover the moisture from coal is called the getting water from lignite system. High temperature flue gas extracted from the upper part of the boiler and low temperature flue gas from the rear of the boiler are mixed and used to pre-dry the raw lignite in a drying tube. Evaporated moisture and coal then enter a beta wheel mill where further drying of the coal occurs. The vapour and pulverised coal are then separated and the vapour is condensed in an ultra-low temperature heat exchanger. Field tests of the system have been carried out on a 100 megawatt unit. And calculations for a 600 megawatt supercritical plant using a version of the system suggest that some 84% of the water vapour in the mill exhaust could be recovered when firing a nearly 40% moisture lignite. And this would be enough to meet the entire water consumption of a dry cooled plant with a wet FGD unit. Commercial systems are available that pre-dry the coal and capture the evaporated moisture before it is pulverised. Two of these are the dry finning and WTA systems. The dry finning system is installed at the Coal Creek station in the USA. It uses a fluidised bed dryer to dry the lignite. Evaporated moisture is currently vented to the atmosphere, but if you installed water-cooled condensing heat exchangers, these could capture nearly 35 metric tonnes per hour of water from each unit. Now, the WTA system also uses a fluidised bed dryer, and a flow sheet of this process is shown on this slide. The heat source for the dryer in this case is low pressure steam from the steam turbine. Right, moving on to ash handling systems. Ash formed during the combustion of coal needs to be removed from the bottom of the boiler. Systems for handling this bottom ash, or is sometimes called clinker ash, can be categorised by their water usage into wet handling, semi-dry and dry handling systems. Today I'm just going to discuss the semi-dry and dry handling systems, which use less water than the wet ones. In wet systems, water is used to both cool and transport the ash. Right, in semi-dry ash handling systems, the ash is dewatered after it's been cooled with water. Recycling this water could result in zero liquid discharge from the ash handling system, as well as saving water. Commercial systems are available, and you can dewater the wet ash either in a batch type system using dewatering bins or on a continuous removal conveyor system. Now, in a dewatering bin system, two bins are needed, and these are used alternately. The bottom ash slurry from the ash hopper is pumped into the top of the bin, and when the ash level reaches a certain point, the flow is stopped. The water is then passed through decanting screens into a separate settling tank. Here, the remaining ash parts are removed and returned to the dewatering bins, and the clear water is then stored in the surge tank before its eventual return to the ash hopper. The conveyor system, which is shown on the right, the bottom ash is removed by a conveyor which is submerged in the water trough below the boiler as the ash is quenched by the water. The ash is then dewatered as it travels up the inclined section. Dry ash systems use ambient air to cool and transport the bottom ash from the boiler, thereby eliminating the need for water. Several approaches have been developed. Now, in some systems, the bottom ash from the boiler falls onto an enclosed moving conveyor belt. The negative pressure in the boiler draws in ambient air, which moves in a counterflow direction over the ash. Sensible heat from the ash is transferred to the air, which is returned to the boiler as preheated air for combustion. And this actually improves the thermal efficiency of the boiler. In addition, combustion of the unburnt carbon in the ash does continue on the conveyor belt, and this therefore improves the ash quality. And some of these dry ash handling systems that are available today, the commercial ones, are listed on this slide. Right, now for pollution control systems. Pollution control systems are fitted to control the emissions of particulates, nitrogen dioxide, sulphur dioxide, mercury, and in the future carbon dioxide. I'm just going to look at the systems for controlling sulphur dioxide. Conserving water in wet electrostatic precipitators and water usage at carbon capture systems are discussed in the in the full report. There are a wide range of commercial FGD processes available for removing sulphur oxides from flue gas, and I can categorise these by their water usage into wet scrubbers, semi-dry scrubbers and dry systems. And wet scrubbers are by far the most common system, with over 80% of installed capacity worldwide. Right, as I showed at the beginning of the webinar, wet scrubbers are the second largest consumer of water in a coal-fired power plant that's fitted with a wet cooling tower. Now, this figure shows a typical limestone wet scrubber system. Basically, a limestone slurry is sprayed into the top of the absorber tower where it reacts with sulphur dioxide in the flue gas. And then compressed air is commonly injected to oxidise the reaction products into gypsum, which can be sold. The water is mainly lost through evaporation and from the generated wastewater. I'm just going to look at the evaporative water losses and how these can be reduced. Right, to give you some idea of the evaporative water losses from wet scrubber, a 500 megawatt subcritical power plant that fires bituminous coal loses over 3,500 litres of water vapour per minute through the stack. An equivalent supercritical plant loses just over 3,000 litres a minute. So water has to be added to make up for the various water losses as indicated on this slide. So one way to reduce evaporative losses from stack is to cool the flue gas before it enters the absorber tower. This can lower water consumption by around 40 to 50%. After exiting the tower, the flue gas is reheated to improve stack gas dispersion and to help avoid condensation and visible plumes. The flue gas cooling system is typically incorporated with the flue gas reheating system to form a regenerative heat recovery system. And these are commonly used in power plants in Japan and Europe. However, corrosion and fouling of the heat exchangers can occur, and parasitic power consumption will increase due to the pressure drop across the heat exchangers. Another option is to recover the extracted heat from the flue gas within the steam cycle. This will improve plant efficiency and hence reduce water consumption. Low temperature economizers are widely used in China to recover waste heat in the flue gas to heat the condensate from the turbine. Right, looking at semi-dry scrubbers, there are two main types that are commercially available. These are the spray dry scrubbers, that are also known as spray dry absorbers, and circulating dry scrubbers, these are also called circulating fluidized bed scrubbers. Right, the water consumption of these two types of scrubbers is similar, and they consume about 60% less water than wet scrubbers. They also produce no wastewater, unlike the wet scrubbers, so no water treatment system is required. However, their sulfur dioxide removal efficiency is lower. It's some 90 to 97% for spray dry scrubbers and just over 98% for the state-of-the-art circulating dry scrubbers. The removal efficiency for wet scrubbers is nearly 99%. However, semi-dry scrubbers can capture more sulfur trioxide and oxidised mercury than wet scrubbers. Now, dry technologies consume no water, or only a minimal amount if the sorbent needs hydrating or the flue gas is humidified to improve the sulfur dioxide removal efficiency. Sorbent can be directly injected at several locations, as shown in this figure. The actual injection location will be plant specific because not all the units shown are necessarily present in every power plant. Unlike the wet and semi-dry scrubber processes, the flue gas is not passed through a separate desulphurisation vessel. Sorbent is injected directly into the furnace, which is shown as FSI in this figure, or it can be injected into the inlet to the economiser, which is marked as ESI, or into the duct, which is marked as DSI. So consequently, there's a smaller footprint and the technology would be easier to retrofit. However, solvent injection systems are best suited to small or medium-sized power plants which are burning low to medium sulphur coals and where only a moderate sulphur dioxide removal efficiency is required. The sulphur removal efficiency is lower than for wet and semi-dry scrubbers. The duct solvent injection processes are being used to control sulphur trioxide and mercury pollutants by using just a suitable sorbent. Right, I'll just touch on multi-pollutant processes which remove two or more regulated pollutants in a single reactor or a single system designed for the purpose. These may be more cost-effective and may lower water consumption than installing a series of traditional systems that remove the same number of pollutants. But unfortunately, these systems are not widely employed. One commercial system that is essentially dry is the REACT process. This uses only 1% of the water required by conventional wet FGD systems and also removes the pollutants which are listed on this slide. And this is actually when burning a low to medium sulphur coal. It's actually installed on a power plant in Japan. Right, I now look at water recovery from flue gas. Flue gas discharged from the boiler contains a large amount of water vapour. The amount depends on the coal type, plant configuration and other factors. A typical 400 megawatt coal-fired power plant in the Netherlands with a wet FGD unit emits around 150 cubic metres of water vapour per hour through the stack, whereas some 90 to 120 cubic metres is emitted when there is no FGD unit. If enough water could be economically recovered from the flue gas, then a dry-cooled power plant could become self-sufficient in water, or in some cases could possibly become a supplier of both electricity and water. It is unlikely that enough water could be recovered to supply the cooling water make-up requirements for a wet-cooled power plant. There are three basic methods for recovering water vapour which are listed here. These technologies are at different stages of development. None has yet been demonstrated at full scale on a coal-fired power plant. Nevertheless, they have been shown to be potentially economically viable, depending on factors such as plant configuration, location, and the cost of water. I'll now look at each of these technologies in turn. Cooling the flue gas to below 50 degrees centigrade, which is the water dew point, would not only condense the water vapour, but also enable the recovery of latent and sensible heat. This recovered heat could be used to increase the net unit power output, and this would also lower carbon dioxide emissions. Condensation can be achieved with direct contact coolers, where the flue gas and cooling fluid are in direct contact with each other, as shown in this figure. Otherwise, indirect contact coolers could be used when an intervening wall separates the cooling fluid from the flue gas. In both cases, condensed water needs to be treated before it can be reused within the plant. A liquid desiccant-based process has been developed and tested at pilot scale by the University of North Dakota's Energy and Environmental Research Center in the USA. Some 50 to 70% of the water in the flue gas from a wet scrubber was recovered. Now, this technology is not new. It is already used in air conditioning units in systems in buildings, and for the dehydration of natural gas, it has not yet been demonstrated on a coal-fired power plant. The process involves cooling the flue gas before it enters an absorption tower into which a liquid desiccant is sprayed. The wet desiccant is then heated before it is sent to the regenerator. The reason for this is that the hotter the desiccant, the easier it is to separate the water. The resultant water vapour is then condensed. The regenerated desiccant is filtered and cooled before being injected back into the absorption tower. The recovered water had a similar quality to that from reverse osmosis treatment, which is normally used to produce boiler make-up water. Questions remain as to the long-term interaction of the desiccant with the flue gas, contamination of the desiccant solution by flue gas constituents, and precipitants that may form and how to handle them. Right, the main advantage of membrane separation technology is the ability to produce high quality water that is mineral free and therefore can be used as make-up water within the power plant without any further treatment. However, net electric efficiency can decrease by about 0.1 to 1.1 percentage points depending on heat recovery and power plant configuration. A modular polymer-based composite membrane system has been developed under the European Union-funded CAPWA project. The membrane consists of microporous hollow fibres coated with a water-selective material. Water vapour permeates through the membranes and is then transported to a condenser by applying a vacuum. At least 40% of the water vapour can be captured. The Gas Technology Institute in the USA is developing a nanoporous ceramic membrane called the transport membrane condenser. It is based on commercial technology that was developed for industrial gas-fired boilers. A two-stage system is being developed for coal-fired power plants that uses two separate cooling water streams to maximise recovery of both the water and latent heat in the flue gas. Right, the last part of the power plant I'm going to discuss is the cooling system, which uses the most water. This is when water is the coolant. There are four main categories of cooling systems that are listed on this slide. Each of these systems involves trade-offs in terms of water use, impacts on water quality, plant efficiency and cost. I'm just going to discuss the closed loop and dry systems. The most common cooling system employed in modern power plants is a closed loop or recirculating cooling tower. The hot water from the steam condenser is pumped into a cooling tower where it is sprayed over the tower fill. As ambient air passes through the warm water, a portion of the water evaporates, cooling the remaining flow. The cooled water is collected at the bottom of the tower and is pumped back to the condenser tube inlets. This figure shows the water flow in one cooling tower design, which is in this case an induced draft cooling tower. Make-up water is needed to replace the water lost through evaporation, blowdown, drift and leaks. The water evaporated in the process forms a water vapour plume and exits through the top of the tower. This loss leads to the build-up of minerals and dissolved solids in the water that can adversely affect performance. So to prevent this build-up, a portion of the water, which is known as blown down, is periodically discharged from the system. And drift is the water droplets carried out of the tower with the exhaust air. As you can see from figures on this slide, evaporation accounts for the highest loss, around 1 to 2% of the recirculating water flow rate. I've also included some figures for make-up water consumption to give you some idea of the amounts involved. I'm just going to look at reducing evaporative water losses. The full report does include blowdown and drift. Right, the warm water in the cooling tower is cooled to a value close to the wet bulb air temperature, which is a limiting factor for process cooling. Cooling to below this temperature could reduce the water lost through evaporation. And this could be achieved by pre-cooling the warm water and or the inlet air. One technology for pre-cooling the incoming air is the dew point cooling tower that's been developed in the USA. Dry channels are incorporated between the wet channels in the tower fill, as shown in this figure. The incoming air is pre-cooled in the dry channels to about the dew point temperature by water evaporation in the adjacent wet channels. The air then passes into the adjacent wet channels where the heat is removed from the water. Now, this system could reduce cooling and make-up water uses by some 15 to 20%. And in addition, power production could increase by up to 4% due to lower turbine back pressure. Pre-cooling the warm water exiting the steam condenser before it enters the wet tower reduces the heat load in the tower and hence evaporative water loss. In the thermo-siphon cooler hybrid system, which is shown here, the heat from the hot water leaving the steam condenser is transferred to a refrigerant in the evaporator and then to the ambient air in an air-cooled condenser. There is no water evaporation. The naturally recirculating refrigerant operates in a closed loop. The system could potentially reduce annual evaporative water losses, make-up water requirements and blowdown volumes by up to 75%. And it could be retrofitted to existing power plants. Other technologies that are at the research stage include the use of thermoelectric coolers, vapour compression refrigeration, and the addition of nanoparticles with phase change materials to the circulating cooling water. Right, substantial water savings could be made by employing dry cooling, which utilises air instead of water to condense the steam. For example, one power plant in South Africa that employs a direct dry cooling system uses about 3.5 million cubic metres of water per year. And this compares to around 50 million cubic metres per year for an equivalent wet-cooled power plant. So this is saving over 46 million cubic metres a year, or if you prefer, 46 billion litres of water a year. Direct cooling uses a large standalone air-cooled condenser. Steam exiting the turbine is condensed within fin tube heat exchangers, which are externally cooled by ambient air. The fin tubes are commonly arranged in an A-shaped frame over a forced draft fan, which is shown in the figure on the left. The system can consist of several rows of heat exchanger cells. Indirect dry cooling is shown in the figure on the right. Here, the steam is first condensed in a conventional water-cooled condenser, and then the heat is then conducted from the warm water as it flows through fin tube heat exchangers in the dry cooling tower by the upward flowing ambient air. There's no evaporative water loss since it's a closed system. The main disadvantages of dry cooling are higher capital costs a lower power efficiency and a larger footprint than a closed-loop wet cooling system of comparable capacity. Overall, plant efficiency is lowered by about 2 to 7 percentage points, and this can be even higher on hot days, though it does depend on the type of plant. This is because air is a less efficient cooling medium than water. Unfortunately, lower efficiency means more coal is needed per unit of electricity, which in turn can lead to higher CO2 emissions. Right, despite the drawbacks, dry cooling is being promoted in several countries and states as a way of conserving their water resources. Technologies are being developed to mitigate the disadvantages of dry cooling. Two technologies that are already in use to enhance power output on hot days are pre-cooling the inlet air and deluge cooling. Both of these use water, but of course a lot less than in wet cooling systems. The inlet air can be cooled by spraying a small amount of water into the inlet airstream of an air-cooled condenser, where it evaporates and cools the air. This is shown in the figure on the left. Some 140 litres per second of water is consumed on hot days during spray cooling at the direct dry-cooled supercritical Cogan Creek power plant in Australia. But doing this does increase power production by 20 megawatts to give a total output of 740 megawatts. Wetted media is less common than spray cooling. Here, the inlet air is cooled and humidified by direct contact with water as it passes through the wetted medium at the base of the dry cooling tower. And this is shown in the right-hand figure. Excess water is collected and recirculated. Both these methods cool the air to near its wet bulb temperature, which improves the performance of the air-cooled condenser, and they're only operated on hot days. In a deluge cooling system, water is introduced onto the thin side of the heat exchanger tubes. And here it runs down the fins as a thin film, and the excess water is collected and recirculated. It requires more water than the spray and wet media cooling systems. A lot of research is being done to diminish the disadvantages of dry cooling and to develop alternative dry cooling technologies. The USA, for example, has 2 research and development programs that are specifically targeting dry cooling, and these are listed on this slide. So, what are the key messages? Water availability is becoming an important issue for coal-fired power plants and will become more so in the future. Therefore, water conservation in power plants will become more important as fresh water becomes scarcer and regulations on water use more stringent. Technologies are commercially available or are being developed to save water within a power plant, but more research is needed, particularly on alternative dry cooling systems. Right, this reminds me to thank you for listening, and to say that the next webinar will be on trends in financing of coal-fired power plants by Paul Burana, and this will be on the 22nd of March 2017. And so I'll just look to see if we've got any questions.
Yes, it seems we have one question. And the first one says, you provided info on water use for subcritical and supercritical plants with a higher efficiency plant using less. What about data for ultra supercritical plants? Okay, Anne.
Right, well, I don't have any figures off the top of my hat, but of course ultra supercritical plants will use less water than subcritical and supercritical plants. I'd have to go back to my report to have a look at the actual figures. But if you like to email me your, give me an email, I can then find the figures for you and send them to you.
Yeah. Okay. And it seems like we have one more question. So it reads, do FGD processes have any effect on CO2 emission and hence water consumption?
Yes, with flue gas processes, if you've got a reagent such as limestone or sodium carbonate, then as they react with the SO2, carbon dioxide is formed as a byproduct. So CO2 emissions will then increase if they're not captured. For spray dry scrubbers, whether you're using a lime reagent, although CO2 is not generated as a byproduct, it will be generated during the production of the lime for the process. So unless the CO2 from the lime kiln is captured and stored, then overall CO2 emissions from the plants will increase. So if you actually install a conventional carbon dioxide capture process like an amine-based process, then the water consumption will go up at the plant.
Okay. And there's one more question. So what about a comparison with IGCC?
I didn't cover IGCC in the report. I only covered pulverised coal-fired power plants. But I do know that water consumption of IGCC plants have been studied. And there was a report published in the USA by NETL which did cover that topic. But I can't remember the precise title of the report.
Do we have time for one more? Yeah, and I think there's one more question. This one? So, what experience is there in flue gas coolers? And is the technology matured, is the question.
Right, I presume you're thinking about cooling the flue gas after it, before it goes into, before it goes into the, I'm trying to work out which flue gas coolers, which part of the system. Right, our information water. The full report where the systems are discussed, when I've got information on the amount of water that can be saved, I do include it in the full report. For the cooling systems, the flue gas before it enters the cooling tower, then things like the thermosiphon system is available from Johnson Controls, which produce it. I just had a thing saying it. They want to cool the flue gas before it goes into the FGD scrubber. Well, if you're using regenerative heat exchangers, that is a mature technology, and that's been well fitted. And I think I said that if you're using regenerative ones, you can save between 40 and 50% of the water. Think about which system it is which you can use. Right, they are actually another system I didn't mention, which they are doing is when you can actually oh, sorry, my mind's gone blank at the time. Right, I just had a quick look at the report, and I was saying if you use your low pressure economiser, let's see. So in China, where they use a low pressure economiser installed, which is between the ESP and the FGD unit, which extracts heat for preheating the low temperature feed water condensate, then steam that would otherwise be used for the purposes saved, which enables more power to be generated. But they did calculate for the 600 megawatt power plant that some 21 to 47 tonnes per hour of water could be saved in the FGD unit, depending on the location of the low pressure economiser. Sorry, I hope that helps reply to your question.
Thank you so much. I think that's all we have time for regarding questions. Thank you again, Anne, for a very interesting talk. The PowerPoint will be available to download later today from our website. And as Anne also mentioned, the next webinar is on trends in financing coal-fired power plants and will be presented by Paul Barua on Wednesday, the 22nd of March. Thank you and goodbye.